So as we have seen today, the definition of iterative function system, just in case let me repeat it for self-affine systems. I will repeat a bunch of other things as well. So we have some, let's say, capital M non-singular B times D matrices, and all of them are contracting, so the norms of them are strictly less than 1. And from these matrices we produce some affine transformations of RD. So it's well known that there exists a unique and non-empty compact set which is invariant with respect to these functions. And we can produce this set by using a ball or by using any kind of closed set which is mapped into itself by all the functions. So, and also for every p probability vector, we can find a unique measure supported on, or at least the support contained in this omega self-affine set, such that it's again invariant with respect to the iterative function systems function and weighted with these probabilities. So these are what I call self-affine systems, self-affine sets and measures, and my point of interest is that what are the values of the dimension of this self-affine measure and what is the dimension of this self-affine set. Both cases I'm interested in the Hausdorff dimension, but the answer will be also the same for the bucking dimension and box counting dimension. So I'm also sure that everybody in this room is very familiar with the definition of Hausdorff dimension of set and measures, but just in case, let me repeat it just to get the essence what we will do in the rest of the talk. So we get any kind of subset of RD, and the S-dimensional Hausdorff measure is A is given by some kind of optimal cover of it. So we take a cover of A such that its cover is small in the sense that the diameter of the covering sets is less than delta, and we take the smallest possible, or very close to the smallest possible value of this sum, radius to the power s, with this cover. So we take in some sense the optimal, and we let that tend to infinity, to 0. The Hausdorff dimension is the quantity which is the smallest s, such that this S-dimensional Hausdorff dimension of the set is 0, and this is also the supremum of s's, where the S-dimensional Hausdorff measure is infinite. And there is a special value which is called the Hausdorff dimension, where can anything happen. For the other case was the dimension of the measure, and this is also related to covers, but instead of covers, let me introduce first the local dimension of a measure. So we take a random probability measure of RD, take a point from for RD, and we so the lower and the upper local dimension, oops, it wasn't a good idea. So the lower and upper local dimension of the measure mu at the point x is nothing as like the shrinking rate of the measure of the ball centered at r when I choose the radius smaller and smaller to tend to 0. This is related to the cover. Oh, cheers. So this is related to cover, and which one is the?
I think middle red, maybe, or
middle red laser. Yes.
Yeah.
Thank you. Is it visible? Yeah. Excellent. So it's related to the covers, like in the following set. So if I define the lower and upper Hausdorff dimension of the measure mu, like the essential infimum and the essential supremum of this lower local dimension, it's the infimum of all the Hausdorff dimensions of possible sets, which can be seen by this measure, which means that actually have some positive measure, and the essential supremum is the smallest possible value of the Hausdorff dimension where can have the set full measure. So this is how it related to the cover, and we call the measure mu exact dimensional whenever this lower and upper local dimension is the same, so the limit exists almost every point. Moreover, this has a constant value at almost every point.
Can I ask a question now? Otherwise, we'll be lost for the end.
Sure.
So this is basically saying if you've got some local dimension that's really outside of the norm, but it's isolated and can't be seen by the measure, then you just ignore it? It's just...
Yes,
Okay.
yes. So there's other studies for this multifractal spectrum stuff. But in the theory of self-affine systems, I think it's quite difficult at the moment. So I don't know too many results, just very few in this multifractal direction. So I ignore them.
Okay.
So, but we would like to prove, and we would like to show that the self-affine measures are exact dimensional, and so we would like to compute the value of the dimension. And from this information, we would like to know something about the dimension of the set as well. So, first, let's try from the other direction. So let's try to cover our self-affine set naively. So what does it mean? We have a ball, and we have a d times d matrix. Then the image of the ball with respect to this matrix is an ellipse. There are two axes of the ellipse. Well, in our D there are d ellipses, which the length of these axes are corresponding to the singular values of these matrices. And by the construction for the self-affine set, we see that at basically the nth level, after n iteration, with respect to the, after n step, you iterate this ball, you get a bunch of ellipses, and basically what you would like to do is cover these ellipses. So there are several ways to cover these balls, but in the what are the naive ways. First, I cover every ellipse by only one ball with radius corresponding to the largest singular value, and then I say that, okay, then when I want to cover this lambda optimally according to the S-dimensional Hausdorff measure, then this quantity is at most something like this at the nth level. What's the second way? Well, try to cover it with balls with radius corresponding to the second largest singular value. Well, you can see that's not a cover, but up to a constant it's a cover. So when I shift it a little bit up, shift it a little bit down, then it's a cover. So in this sense, it doesn't matter too much. But in this case, how many balls do I need really to cover this ellipse? Well, approximately alpha 1 over alpha 2, which is that how many balls do I need to cover it, but as many as alpha 1 over alpha 2. And this is my new quantity for the upper bound of the S-dimensional Hausdorff measure. So, well, and I'm very bad at drawing things larger than d equal to 2. So we can generalize this idea as follows. So for matrix A, we introduce this singular value function, which S here, and this alpha SA corresponds to the radius of the ball, and this guy, times alpha S to the power minus S, corresponds to the number of the balls, what I need. And by using this, we can define a so-called subadditive pressure, which is I sum up the singular value function according to all the possible matrix products from here, and I take the logarithmic shrinking rate of it. And I'm interested in those S, which is the root of this pressure. So Falconer proved that because it's basically produced a naive cover, that's in every case the Hausdorff dimension is at most the affinity dimension. Moreover, if we fix our matrices and choose the translation vectors to be a Lebesgue typical vector, then the Hausdorff dimension is actually the minimum of D and the affinity dimension. I must put this D here because the dimension of the set cannot be bigger than the state space. And what can we say about the dimension of the measure? First, to be able to speak about the dimension of the measure, we need some symbolic things. First, we define what's the symbolic coding of the points. So I have capital N functions, so I need capital N symbols, and I take to the space of all infinite sequences from the symbols 1 to n, and for this infinite sequence, I map this infinite sequence to a point on the attractor on the self-affine set by choosing this intersection. So this is a singleton because I have contractions. And if I choose a probability vector, and I choose nu to be the Bernoulli measure on this sigma symbolic space, which means that I define the measure of the set such that I fix the first n symbols to be the product of this pi1, pin, etc. Then this is what we call a Bernoulli measure. And when I push down this nu measure onto the attractor with respect to this pi, which I would call the natural projection, then what I actually get is this self-affine measure. So this will be invariant with respect to the measure, and since it's invariant and since it's unique, then basically we have found the only self-affine measure. So what can we say about the dimension of it? So we have this probability measure, we have the Bernoulli measure, we have everything. So we can define the entropy of it in a very usual way. And from the oscillator's theorem, we also know that for a typical product of the matrices, the ith singular values logarithm, or times 1 over n, converges to a value which is called the ith Lyapunov exponent for the typical sequence of symbols. I put here this minus just to confuse you a little bit and just to get this Lyapunov exponent to be positive. And then, by the definition of the singular values, you can see that psi1 is the smallest and chi d is the largest, and basically strictly bigger than 0. So, like very similarly to the naive cover for the set, we can define a so-called Lyapunov dimension of this self-affine measure, which is this quantity. So basically, it really corresponds somehow to the subadditive pressures root, the affinity dimension. But the most important point of it, that Jordan, Policott, and Shimon proved that actually the upper Hausdorff dimension is every time, regardless of your matrices and your translations, is at most the Lyapunov dimension of the mu. Moreover, they showed a similar statement like Falcon and Solomiak. So if we choose the matrices such that the norm is less than 1/2, then for almost every choice of the translation vectors, the Hausdorff dimension of mu is actually equal to the Lyapunov dimension of mu. So it's okay, very good. But what can we say in general? And can we examine the question in another point of view? So here, every time we fixed our matrices, and then we just chose typical translation vectors. Can we do in opposite way? Fix the translation vectors and choose your matrices randomly. Well, the answer is yes, in some cases. So, and it's quite surprisingly non-trivial, and we need a bunch of new tools to get rid of this problem. So the first new theorem is from 2015, and surprisingly 2015. And I'm amazed that this theorem is from 2015, which says the following, that there exists an open and dense set of matrix tuples with full Lebesgue measure, such that for every Bernoulli measure mu, the Lyapunov exponents are distinct, which means that it has a simple Lyapunov spectrum. Whenever you ask someone, oh, it's trivial. It's absolutely not trivial. It's a really, really hard machinery to prove it. The other machinery is, other thing is so-called Furstenberg measure. Because you have these matrices. These matrices are ellipses, and it has directions. We need some control over these directions, and if you have in RD, then this control gets worse and worse. However, there's this theorem of Karoly, which says the following. So let's take the space of legs of RD, which means that this V d minus 1 is a one-dimensional, so this is the GKD represents the Grassmannian manifolds of key-dimensional subspaces. So here's this G1D, this is a one-dimensional subspace, the next one is a two-dimensional, which contains this one-dimensional, etc., etc. So this is why we call it a flag. And V1 contains everything below, and it's a d minus one-dimensional subspace. So this theorem says the following: if you have a simple Lyapunov spectrum, then there exists a measure mu f its support contained in this F space of flags, such that it's an invariant and ergodic measure in the following sense. So actually, mu times mu f is invariant and ergodic with respect to this t transformation, where t is nothing else than in a first coordinate in the infinite sequence of symbols, you just apply the usual left shift. And here, for this flag of subspaces, you apply your matrix, the inverse of your matrix, according to the first symbol. And secondly, for almost every pair of infinite symbols and subspaces and flags, if you are interested in the growth rate of this inverse matrix product on this ith subspace, it actually corresponds to this sum of Lyapunov exponents. So you have now control how the matrices are growing on this ith subspace, but of course it must be a typical subspace. And finally is the so-called Ledrappier-Young formula, what we need. The Ledrappier-Young formula says that the self-affine measure, if you have simple Lyapunov spectrum, is exact dimensional. Moreover, we can write up the dimension of mu as a function of the entropy of nu, the Lyapunov exponent with respect to nu, and two other things, this capital H, which is I like to call as a conditional entropy, which means that it measures how many points are above 1 point. So this is actually a conditional measure on the inverse branch of I. So actually, so let me just read. So mu I is supported on I inverse of P of I. So it's a conditional measure on these slices, basically. And so the difference of the entropy of nu and nu is basically lies inside of this capital H. So this is how the entropy can draw. And on the other hand, it contains a bunch of dimension of other measures, which are basically projections along subspaces, not onto, but along subspaces, along the ith subspace in this flag. This is the orthogonal projection onto the orthogonal complement of Vi. So this is what we know, and these are all tools, but there is a nice consequence of this Ledrappier-Young formula, which means that we can be pretty sure in the following, that the dimension of mu is equal to the Lyapunov dimension of mu if and only if this H, this conditional entropy here, is 0, so the entropy does not drop. Moreover, for almost every subspaces, for almost every flags, if I'm looking at the orthogonal dimension of the orthogonal projection of mu along this Vi, this also does not drop, which means that it must be the minimum of I, which is the dimension of the state space, and the dimension of mu, which is the dimension of the original measure. So this is an equivalent characterization of having Lyapunov dimension, and there is no dimension drop in any sense. So the hardest problem is how to get rid of it. And basically the strong open set condition is a possible tool. So if there is a strong open set condition, which means that I can find an open set such that the images with respect to two different functions from my IFS are disjoint, and U is mapped into itself by all the functions, and the attractor and this open set, the intersection is non-empty. That's a really important thing, that the intersection must be non-empty. Then we know that this conditional entropy must be 0 because, well, then almost every point is basically has a unique inverse image. Okay, how can we can say something about these things? Well, the first case where we can say something is the planar case, which means the following. So there is a quite old result of Falcon and Kaufman for general matrices, for general Radon measures. It says that if I have a mu, it's a measure on the plane, just a Radon measure on the plane, and if I want to project it along subspaces, but I choose this subspace according to a measure mu f, this theorem says that if the dimension of the mu f is large enough, which says that greater than the minimum of the dimension of mu and 2 minus the dimension of mu, so we really have some chance that the dimension of mu f is large, because this guy is at most 1. Then there is no dimension drop, which means that the orthogonal projection of this measure is equal, the dimension of it is equal to the minimum of 1 and the dimension of mu. So this means that there's no dimension drop. In the self-affine setting, Ledrappier showed that instead of taking here the dimension of mu, you can take here the Lyapunov dimension of mu, which is much, much better. Since basically I'm interested in the value of the dimension of mu, and I need to produce some condition where this dimension of mu is already involved. That's something very bad, but here you can omit it and simply use the Lyapunov dimension, and you have the safe statement. So the problem is how to calculate the dimension of this measure mu f. So we are on the plane at the moment, which means that I don't have actually flex. My measure is only supported on the projective space. And this is basically now corresponds to a conformal measure on the projective space. And Hochman and Solomiak, oops, too much. Hochman and Solomiak showed that if your matrices satisfy a so-called Diaphragm condition, which means that there is an epsilon such that if you take two different products of the matrices, and you can take the difference and take the norm of it, it must be at least epsilon to the power n. So this is what they call Diaphragm condition. But if you have this condition, then you know that the dimension of mu f is equal to the minimum of 1 and the entropy over the difference of the Lyapunov exponents. So we have only two Lyapunov exponents again, since we are on the plane. But then, this means that you have something computable. You really can compute something. Which leads us to the Morrison-Schmerkin theorem, which says the following: if you have strong open set condition and this Diaphragm condition, moreover, you have this assumption as well, which is equivalent to that the affinity dimension is larger than 3/2, or you have this other condition, which is called one bunch condition. If these two things hold, then you have that this value is smaller than this value, which means that the Hausdorff dimension of my self-affine set is equal to the affinity dimension. Okay, but there's one huge problem at the moment with this Diaphragm condition, that we don't know at the moment how typical it is. Of course, we can guess that it's very, very typical, and that's a correct conjecture, I think, but we don't know at the moment. So to handle the problem that we take typical matrices and look at typical matrices, in the first problem we choose our matrices with positive elements. So I choose my 2 times 2 matrices, all of them has positive elements, and then this mu f, self-conformal measure, basically corresponds to this nice conformal iterated function system on the interval 0, 1.
So you have 5 minutes, okay?
5 minutes, that's more than enough.
Okay.
Okay, so you have this nice iterated function system, and by using the standard transversality methods, you can prove what happened, I think. Okay, so if you choose your matrices that the determinant over this nasty value square is less than 1/2, which basically means that the contracting ratios of these functions at every point of the interval 0, 1 are less than 1/2, then for almost every choice of the elements and almost every choice of the matrices, you can calculate the Furstenberg measure, which is exactly the same quantity. And then again, you have this already seen conditions, this one bunch at the affinity dimension bigger than 3/2. You can say that if the strong open set condition holds, then for almost every choice of the matrices with positive elements satisfying these things, the Hausdorff dimension of the attractor is equal to the affinity dimension. But there is another method where we don't want to involve the Furstenberg measure. We don't want to involve this measure on the space of flex. And how does it work? Fix some translation vectors and take your matrices, again we are still on the plane, take your matrices such that the matrices satisfies this nasty inequality. This nasty inequality is nasty, but it has some nice geometrical meaning, which is the following. Take a ball. This ball is mapped into itself by all the maps, and these are the images of these balls. Now take the balls, smallest balls, which are containing these cylinders, and if you draw these tangent lines, the angle between them must be strictly less than pi/2. That's the geometrical meaning of this nasticity. And then, what can you prove? What we can prove is that the dimension of the self-affine measures and the dimension of the attractors are the Lyapunov dimension and the affinity dimension for the typical choice of matrices from this regime. And what can we say in higher dimension? Because in higher dimension, we don't even have any idea how to calculate at the moment the Furstenberg measure dimension, the dimension of the measure in this space of flex. Oh yeah, and a remark that this is actually something independent from the dimension of the measure mu f. So there is an open subset of this guy such that there's no chance that the previously seen condition holds. But still we know that for almost every choice of the matrices our theorem holds. And finally, in higher dimension, what we get is a little bit worse constant here. But we have basically the same theorem. And thank you for that.